Hello, everybody. Before we begin, let me introduce myself briefly. I am Nhan, and I am a researcher of Air Defense Air Force Technical Institute in Hanoi, Vietnam. Today, I'm going to be talking about our topic, calibration of phased array antenna with the minimum point finding method of the array factor. I will begin by introduction and then I will talk about the proposed method, results, and discussion. Finally, I will give a conclusion of our work. We know that phased array antenna plays a very important role in model radar and communication systems. The efficiency of the phased array antenna is processing the signal reflected from the target is contingent upon the state of the signal receiving channels. Consequently, the asynchrony in amplitude and phase of the received signal between channels significantly impacts the accuracy of subsequent signal processing. This asynchrony is due to different channels delays, signal attenuation, channel noise, external impacts, and many other factors. This problem is solved using various calibration methods as calibration lies, peripheral fixed probes, geocoupling, and rotating element electric field vectors. Unless real-time on-board calibration is necessary, the calibration method based on lookup table generated by an initial calibration at manufacturing level might be sufficient. The rotating element electric field vectors method has advantages in terms of accuracy and system complexity. This method rotates the phase of each element of antenna from 0 degrees to 360 degrees and finds the maximum point of the array factor. However, the problem with the traditional RF method is the small dynamic gain with respect to the change in phase around the maximum received power. The system cannot find the correct phase calibration values due to a small power resolution near the maximum point of combined electric field vectors, which cause the calibration errors. A calibration method in the initial factory level aims to have a high accuracy, and it is essential to investigate and develop a novel approach based on the RAP method that enhances accuracy and simplifies the system complexity. Next, I'd like to talk about the proposed method. The concept of the proposed method is based on the array factor equations. Figure 1 shows a diagram to describe the array factor of the phased array antenna. We can write array factor as formula number 1, where is the complex incident wave equation at the nth element. Omega is the complex representation formula for amplitude shift and phase shift. In figure 2, we consider the case where all array elements are separated by the same distance d. And we can see that the phase of element m plus 1 leads that phase of element m by some phi equal kd cos theta, where k is a wave number. Since the path length to element m plus 1 is a decos theta meters longer than the 2m. Then if we set the reference point to element 0, we can write the array factor as formula number 2. Consider the case where each element of the array is excited with a signal at an amplitude of 1, but because the transmission paths between elements are not equal, the phase shift of each element will be different, and we can write the array factor as formula number 3. Then, to determine the phase shift gamma using the minimum point finding method, we need to find angle gamma at the minimum point of equation 3 as formula number 4. Let's move on and discuss the simulation of proposed method. For number of array equal to the array factor can be written as formula number 5. And to determine the phase shift gamma, we use formula number 6. The simulation results when using MATLAB show in figure 3. We can find the angle gamma at the minimum and maximum points of the dependence. With the minimum point finding method, when the angle of incidence theta equal 90, the phase shift gamma equal 0 degrees. In the subsequent step, in figure 4, show an exemplary calibration scenario is simulated to describe the proposed method. The reference antenna and antennas to calibrated are distant from each other in the near field region. The reference antenna is aligned toward the middle of the two antennas to be calibrated to accurately detect the minimum point of the array factor. Figure 5 shows that the dynamic range of the calibration magnitude by the proposed method over the 60 degrees phases around the minimum point is approximately 42 decibels, whereas the RevMax method demonstrates a dynamic range of 2 decibels around the maximum point method. Figure 6 demonstrates that the minimum point finding method exhibits superior phase calibration accuracy in comparison to the maximum point finding method, with a difference of 15 degrees. At this point, I'd like to turn to results and discussion to experimentally test the mathematical model of the minimum point finding method. A series of experiments were conducted utilizing a calibration system design. Figure 7 illustrates the calibration system for determining the transmission characteristics of the proposed array when using different methods. The reference antenna and calibration receive antennas are distant from each other in the near field region. The reference antenna is aligned toward the middle of the two antennas to calibrate it. Figure 8 shows signal processing block, which includes AD93, one-card control board, CSC70 board, and the signal received from the two receiving antennas using the AD93 one card, and then the signal from this card is transferred to ZC 706 card to determine phase shift or draw the radiation pattern of the received signal on the laptop when using rep mark rep min methods and non-calibration. Further, the entire calibration system was controlled through the designed graphical user interface as shown in figure 9. Figure 10 demonstrates the calibration systems for drawing the radiation patterns of the proposed array after performing the phase shift of received signals by different methods. In this case, the transceiver antenna and the calibration antennas are distant from each other in the far field region. Subsequently, the proposed system will be compared with the traditional ref method. We set the distance between two calibration receive antennas D equal 0.625 lambda, the distance between the phase array antenna under calibration and the reference antennas was 0.07 meter, which satisfied the near field criteria at 3 gigahertz. Figure 11 shows that the received magnitude dynamic range across the 60 phases. In addition, and the ref meters was approximately 35 decibel and 1 decibel respectively. In addition, when the angle of incidence theta equal 90 degrees, the proposed calibration shows a maximum deviation of 5 degrees, while the ref method shows a maximum deviation of 70 degrees. Figure 12 and table 1 show upon doubling the distance d between elements of the array, the peak and width of the side lobes also change. Different noise has a relatively large influence on the radiation pattern of the combined beam. However, the minimum point finding method still ensures a better radiation pattern than maximum point finding method. Let me return to an earlier topic briefly. The work proposes a new rotating element electric field vectors calibration method that can effectively improve both the accuracy and complexity of the system. The proposed method is distinguished from exciting methods by using the minimum point finding method of the array factor. Therefore, the proposed method can be considered an effective solution for large-scale phased array calibration systems at the production stage. Thank you for your attention. Should you have any questions or concerns, please get in touch with me. I look forward to hearing from you soon. Thank you very much.